morning, one and all, and welcome to last session of the summer this research summer workshop on the recent algorithms for remote sensing application. So today, the last session, we have resource person, Professor RamaRao N. He is a professor and head Department of Earth and Space Science at Indian Institute of Space and Technology, Trivandrum. Before start of, answer is going to talk about deep learning algorithms for high resolution remote sensing data analysis. And before I start off his lecture, I request Basaraju to introduce a speaker.
Very good morning to all. Welcome you all to the second session of fifth day workshop. And I'm very happy to introduce our resource person, Professor RamaRao Nidamanuri. So Dr. RamaRao is professor in remote sensing and image processing in Indian Institute of Space Science and Technology, Department of Space, Government of India, Thiruvananthapuram. Professor RamaRao is also a visiting professor at University of Kassel and Leibniz Center for Agriculture, Landspace and Research, and has been Alexander von Humboldt Research Fellow, Germany. Dr. Rao obtained MTech from Birla Institute of Technology, Mishra, Ranchi, and PhD from Indian Institute of Technology, Roorkee, on hyperspectral image processing in 2006. So, after a brief stint at RMSI Private Limited as a project leader, Dr. Rao moved on to continue academic pursuits in RMIT University, Australia, and Leibniz Center for Agricultural Landspace Research, Germany as a research scientist during 2007 to 2010. During this period, Dr. Rao performed research studies on hyperspectral image processing and analysis methods and developed several new hyperspectral data analysis algorithms. Results of these studies are published in several peer-reviewed journals published by IEEE, Elsewhere, Springer, Taylor and Francis publishers. He has been an active member of several professional societies, including senior member of IEEE and is the founder chair of the IEEE Geoscience and Remote Sensing Society Kerala chapter and chairman of Indian Society of Remote Sensing Kerala chapter. So, composed of several doctoral and master students, Dr. Rao's research team has been working on the real-time classification, automation, target detection from the military, agriculture, water, and forestry using high and ultra-high spatial and spectral resolution remote sensing data from terrestrial drone, airborne, and satellite. So, lidar point cloud and 3D modeling of the natural and built environment, open architecture, and regional sensitive atmosphere correction models for multispectral and hyperspectral imagery across platform. So we are very happy to have Professor RamaRao as the resource person. On behalf of everyone, I once again welcome Professor RamaRao and I request you to take over, sir. Thank you.
Thank you. Thank you very much, Mr. Raju. Thank you, Dr. Samdar, for inviting and for the opportunity given. Good morning to one and all. Thank you for joining the session. In this session, I would like to share with you some of the different kinds of remote sensing applications that we have made as part, which included adapting and applying some of the typical machine learning and even the deep machine learning algorithms to uh, derive some sort of analytical perspectives and analyze the remote sensing images. So it's a mixture of different applications and how these some of the evolving machine learning, or we could say deep machine learning algorithms have been used and they have been modified in that process to adapt to the kind of demands of that particular application. So as you know, it's nothing is a single person's contribution. We always have been deriving our strength and works from a dedicated team, which included some of the master students and PhD. And of course, we get a lot of funding. In the sense, most of the work have been possible because of the generous funding from different agencies. So I would like to put on record my acknowledgements to each and everyone who contributed to some of the works which I like to present. I would say on behalf of the works that I have done. So I'll be presenting like that. Generally, in this content, it's more of a generic in nature. I would like to start with some concept of publication perspective and involving some of our young students, particularly undergraduate students to first year masters, and some of the applications that we have been working on that, which included 3 to 4 kind of categories. So, which encompasses the kind of algorithms that are there in this particular event. Generally, we deal with mainly from images, so and point cloud. So LiDAR point cloud. I guess most of you are familiar with the LiDAR remote sensing. So that way, we could consider that as a LiDAR point cloud. And then the remaining things that we talk about is mostly using images. So be it multispectral imagery or even hyperspectral imagery. So we will talk about images. So generally, we can put at a very broad level the types of works that we can carve out of any image or data sets are for 2 or 3 purposes. One is this mapping purpose. Let us say identification of a particular kind of class or a set of classes and their spatial temporal nature. If we call that mapping, we generally realize that kind of mapping job by a typical classification problem or a detection problem. So these are the detection and discrimination, you call both of them. So these are the problems which are taken care as an algorithmic perspective. So whenever we like to do any process related to mapping, we adapt either classification problem or a detection problem. On the other hand, if we like to have some sort of estimation, for example, estimating water content in soil or estimation of, let's say, a particular kind of gas molecules or concentration in atmosphere, or estimation of, let's say, uh, organic content, or let's say any kind of parameter that you like to have, be it geophysical or biophysical, any kind of thing. If you like to retrieve it, then that is called estimation. So this estimation problem is generally approached through a regression way or a prediction problem. So these are the statistical or any pattern recognition methods which would give us the way to estimate. Apart from this estimation, there also has been some cases where modeling is one of the main approaches. For example, if we like to derive a system which would be taking care of all these atmospheric corrections or abnormalities of remote sensing data acquisition, then we are going to model the system such that it includes the behavior atmosphere and the composition of images which respond to different kinds of parameters atmosphere, and then finally making a model which would take care of some of these corrections. Similarly, you can also have another way of looking at the data sets or works where you're actually simulating different kind of systems. For example, if you like to have an imagery which is going to be looking like on a particular day, particular time, and a particular environment. So you know at time t, but if you like to visualize similar kind of data, if the parameters of your play are different, then how it is going to be. So generation of such kind of scenarios is what you call simulation. So which again has both abstract and quantitative way of doing the thing. So in all these kind of works, we can say that most of these point cloud or images form the basic data ingredients and approaches which are classifications or detections or regressions or predictions or even simulation and modeling and optimization techniques are the ones which are usually adapted to realize those problems. Uh, just just broadly putting one more categorization, we can have 2 3 ways of looking at the problem that we like to anticipate. For example, there are 2 ways. One is the static and repeatable, and based on the way that you compute. For example, if you like to classify a simple land use map, or it can be an urban or even state or international thing, then if you have time, so that time can be of order of several days or months. So there is nothing that is really time critical that forces you to do that thing in the next 15 minutes or 5 minutes. So once something is done, you are going to repeat it the same way. You have got plenty of resources, plenty of competition and human resources, then you will achieve the target. So a routine way of looking at the thing. Another way is that those are actually very dynamic in the sense if you like to simulate the way this flooding is going to happen with the next 1 hour based on that kind of data that you have just 1 hour before, then the problem that you have is that you do not have resources that you require to be sitting comfortable in lab and getting data into your computer and waiting for you to have them analyzed after a few years. So they are very critical in the sense the need for analytics and information is order of minutes or seconds. So that way your ability to intervene is very limited. So you cannot have a lot of human resources deployed. And the computation time, you cannot wait for days. You cannot wait for hours as well. So it is very fast. So then obviously you get to have data which is actually a stream instead of an isolated data sets. You have got a stream of data. So flooded with those kind of things, how are you going to cope up with this kind of scenarios? So most of the applications fall on either this of the categories, and sometimes we will be looking from different ways of handling this application. Then if we just before I venture into another thing, if I like to put three most common issues that limit application of any advanced machine learning or deep learning approaches in remote sensing data analysis are actually these three. First thing is that you always get a limited number of samples. Samples does not mean that it's only do not mean that it's only pixel. It can be pixels. It in the case of a classification. So let's say reference pixel. Whereas in the case of let's say estimation, for example, if you like to estimate the kind of let us say urban for example the quality of a plant health or let us say a chlorophyll content of a plant, then you have got certain kind of reference measurements taken, so which could be based on whatever you take measurement and take it to lab. So in that case what happens is that your laboratory analysis samples are always limited, so that way you do not have got a lot of, so it's always a problem. And sometimes you may have some samples which could be pixels or it could be laboratory measurements, but those are either too big or too short depending upon the data that you are going to use to further analyze. So data space also derives that kind of question. So you have got scenario where you say that always a limited number of samples, either images or even measurements. Then many things that we do, whatever technique that we apply, it sometimes is specific to that kind of image alone or that particular kind of a sensor system alone. So it is not transferable where you can do the similar kind of problem if the data sets are quite different or even if the same kind of data but from a different sensor. So these are another set of problems. And most important thing is the time constraint. So you cannot have processing done for several days, or your application time requires that you would be getting this analyzed images in order of few seconds or milliseconds. So these are some of the typical constraints which actually challenge the way we like to devise applications based on these deep learning techniques, or we call simply deep machine learning techniques, and particularly using those kind of techniques to analyze the most sensitive data, which are huge, let's say by volume or by its dimensionality or the way it changes. And then, just before I start some of the application perspectives, I would like to draw some of your attention to some of these global scenario of publications. So, if you look at many times we do research, and sometimes we publish, sometimes we think that we should be doing. Sometimes we feel that okay, we can go ahead. So, where we stand. So despite several reasons for doing or for not doing, if we like to see a link between doing research in terms of remote sensing or any other area and where we stand as a country, if you see, uh, there has been several interesting facts of this publication and research funding, because anything that we do has some bearing on the way it is funding is managed. So if there is hardly any publication output in a particular discipline, it indicates that it is not getting any due credit of funding, so which is a big problem. So if we like to have good, let's say, funding derived, then we should also be looking at the way at nation level a kind of publication outcome derived in that area. So in that thing, just if you look at health research is the one which is very dominant across the countries, just across globe. And India, unfortunately, we have got some scenario where nothing is something very certain. So it's not following the pattern. So, but one positive factor is that some of the engineering disciplines get same weightage as other kind of thing, particularly this computing as well. So there is some pattern which is not at par with the global pattern. And we just see what is the scenario during last, let's say, 18 years. So, or 10 to 18 years. If you look at it, there has been tremendous growth in the quantity, in fact, as you can see, in terms of absolute number. So when you normalize with respect to number of institutions and perhaps persons, of course we cannot be standing, let's say, the way we like to. But if you see that there has been very substantial growth in the way this absolute year-to-year percentage there. So that's a positive sign. But still, we are in this group of lower middle income countries where the entire volume is about 9%, still far away from joining the league, which is, let's say, upper to middle higher income groups. So we require to understand that we still have a lot of potential to increase our numbers. And in terms of the quality of publication, for example, if you take the top 1% best publications, then there has been some shift in the way downward, particularly to India. When we were relatively better some 10 to 15 years back, now we are actually a little bit going down. So perhaps we need to think what is the reason. But the index says that India is really now concerned about enhancing the quality of research, in the sense publication from perspective. While numbers are also important, at the same time, the quality is also another factor that defines how we move actually ahead. And one of the things that also differentiate and help us to move ahead is that collaboration, actually both domestic as well as international. If you look at the recent trend of publications, for example, if you take last uh, 5 to 7 years, the shift has been more of an international collaboration. Many publications or most of these top publishing countries have been doing with the collaborations outside a foreign university or foreign other. So that way, you can see that most of these top performing countries in terms of numbers, let's say the China or UK or US or even Germany, the number of publications from collaboration is much higher compared to the domestic collaboration. So that indicates that a lot of networking has gone and a lot of networking produces good quality and number publication. Whereas in the case of India, its trend is very much similar to some of the restricted countries such as Iran, Brazil, or South Korea. Somewhere you find that these international collaboration or across domestic collaboration is not that active, thereby limiting the numbers, both quality and quantity. So this calls for joining interdisciplinary research. So we need not to be looking as interdisciplinary. So it's a transdisciplinary kind of research, so that the way we think can be adapted to the changing demands, and the problem solution always has multidimensional way. That way, a more pragmatic approach of conceiving research in geomatics helps to find out more outcome and achieve better perspectives from engineering versus science. And in this way, we have been actually, world has been moving from multidisciplinary to transdisciplinary so that you would not find out what is the field that you are looking for. So you that is where this present context of geoinformatics stays, where interdisciplinary to transdisciplinary, multidisciplinary has gone already. So the way we conceive the works and joining together and the way this world is moving is actually far away from interdisciplinary. So we find that nowadays it is not something appropriate to call I belong to this discipline or that discipline. So it is rather the work that defines. And one of the things that are resources which are poorly used or actually often ignored is that these undergraduate students, and particularly first year MTechs as well, we tend to think that it is just a project or not necessarily thinking leading to producing an outcome of publication, which is sometimes, in fact, unfortunate situation. But if you see, most of these recent contributions since of technology breakthrough are actually from undergraduate research. So most of these undergraduates are underutilized. But if you see the enthusiasm, the energy, and the way the creativity comes, that is one of the best sources of energy to derive. And you can see that the world is moving to see that young researchers are leading the way these innovations are happening. So that way, we just have to relate how these undergraduate students have been, deployed in research. So this is one of the data set that I analyzed, taking different undergraduate students and looking the way. If you look at it, most of these well-producing, particularly these research outcome producing, be it publications or some other scientific reports, if you see the involvement of PG and UG, their relative comparison not that much. Let's say it's a maximum double at most. Whereas in the case of India, it is like a 5 to 7 times difference, which shows that all these young students are actually not utilized at all. So that is a perspective difference that we need to consider. And as you can see, from worth of publication, if you see how that has been involved and that the involvement led to publication, the trend is similar where the involvement of publication from UG is very poor, whereas in other case where there is involvement high, publication of UG and PG are really not really abysmally different. So they are very close. It indicates that somewhere we need to think that lot of manpower is available in different form. Perhaps we need to tap it in differently. And we know the most of the reasons. So we always have this unfortunate way of looking at short-term goals, and which continue to be like that. So that is one of the reasons where we tend to ignore some of the agri researchers into putting them or involving them into research. So I like to appeal to all of you that we should be realizing to mean that we need to take care of some of the young energy into this research involvement so that there will be a day where they can also be as productive as some of the master students as well. Now, coming back to the theme of the talk, where we like to see some of these deep learning applications have been, or deep machine learning algorithms have been applied or adapted and made into a process flow for deriving some of these typical remote sensing applications. So the first thing that comes into this is actually agriculture is one of the common domains where every time we start and end there with. In that, the problem is that we like to have some things done on the go. And perhaps you can see any technology intensive agriculture crop growing practices require that some of the things, for example, identification of patches which require attention or the health of crops on a large area requires you to get the data on the go. It cannot be something like you acquire images, go home and analyze them later. So that is not going to happen nowadays. So you like to see that things that happen on the go. If that is the case, then what happens is that the first problem that comes into is the identification of the nature of that crop. what is let's say type of the crop, what crop it is, whether it's rice or sugarcane or vegetable crop, such kind of identification is one of the first things that come into play. So in that way, if you like to have some system where you acquire images, maybe like a stream, which is a sensor mounted on drone based kind of platform. And if the images come as a stream, then how would you be responding in terms of your ability to analyze them on the go? Is one of the classical problems that has to be tackled. So in that case, we just have made some experiments, in the sense acquiring data sets using drone-based hyperspectrophotometry. So in a sense, this airborne is one of the other alternatives, but based on some of the considerations, we have got some experimental setup done and images are required, drone-based hyperspectrophotometry, and we try to see we try to evaluate the potential of some of these deep machine learning applications or algorithms to make a way for analysis of these images which are variable by, let's say, height difference. Maybe the content of the images will be differentiable by the number of crop that each image contain, and like that. So if we like to analyze these kind of images on the go, how do these deep machine learning techniques work? How do they respond? Is one of the applications that we tried. And we know some of the agriculture, you have got both the problems. You have to estimate, for example, if you like to estimate less nitrogen content in a plant so that you can optimize your, let's say fertilizer application, be it soil or plant, you have got an estimation problem. At the same time, you have a discrimination problem as well. What crop it is? Sometimes you may find that two different crops are spectrally very similar, but they are actually structurally very different. So you get some of these problems as well. So considering that these things are there, how do we plan a way to estimate some of the things and move on? So if it is going to be a multi-date, then it's a additional challenge to look at that the way these data are organized and the patterns are mined to find out how they look like. So in that way, remote sensing has a lot of potential to apply this precision agriculture, be it estimation problem or identity mapping problem or even prediction problem. So prediction is slightly different compared to the first two things, so that you don't have a tangible input, but you like to predict based on some kind of data that you have derived. So this is one of the things that we made in the data analytics. The sense different crops are grown with a different kind of treatment, nitrogen application, and then airborne, sorry, a drone and ground-based lidar point cloud have been acquired and tried to analyze the plant level status of nitrogen and discrimination of these crops at the individual plant level. So of course, we are very closer now to the hyperspectral images. As you can see, the imaging is now at a very precise level. You will have less than 1 nanometer spectral sampling. That's what you get. At the same time, you get images. If you mount a drone, you get the images which are of few millimeters of resolution. That is the standard now. So that makes us to believe that the hardware technologies has surpassed the way that we like to look at the way our ability to analyze. So earlier it was reverse. You have a lot of resources, human resources to do, but the hardware is limited. Now it has actually a reverse problem. So how do we cope up with when this kind of images are there and to derive applications which are not something like a regular fit? For example, any kind of indoor, these are all hyperspectral images where you can have very precise resolution and structural details of objects. Then you can have estimation or prediction or classification problem solved. So we have a lot of the data acquired, and then try to make a way where some of these common deep machine learning algorithms, for example, CNN algorithm network is one of the common approaches that is widely used. So using that kind of network or adapting that network to do a function of actually applying a kind of a crop. For example, if you acquire an hypersphere imagery which contains only one plant, then identifying them, what is the name of that particular plant or the crop type is one of the problems. And then if we have got an image instead of one particular crop plant, if we have got an image which is now complicated, again hypersphere imagery, but the image is such that it varies by scale, it varies by resolution, and then it has multiple plant objects. So if you like to identify what crop it is, considering that it has some other background of, let's say, information classes as well. So differentiating the kind of crop from a plant level perspective is one of the challenging applications of remote sensing. So within that specific, if you can have possibility of your images of different crops. For example, your image may contain a single crop, or it may contain multiple crops, or it may contain images of different crops which are quite different at phenology stage. So all those possibilities are there. And adding to that, images are acquired, usually at different altitude. So you may get an image data set wherein images are acquired at multiple distances, let's say 25-meter, 40-meter, 100-meter altitude. That way, the data sets are quite differentiable by their resolution and their perspective geometry. So if you have such kind of image data sets as a stream, how are we going to devise a technique which identifies the crops automatically is one of the problems of this and evaluating these deep machine techniques for crop classification. So we have evaluated some of these deep fully connected networks, which are part of this DCA network with slight variation, wherein image crop objects have been given as input training with a very deep network training, which included giving patches of several thousands as the training library, and which also contained different crops and different stages. And finally, once this training is done, these crops are actually predicted for identification of crops which are at quite different stages. For example, the test images could be extracted from different altitude, or it may contain a different types of crop against the background. So how that prediction happens is one of the applications where we try to differentiate these crops with a deep neural network thing. So as I mentioned, here our aim is not to develop this deep machine learning as such. So how to adapt it, how to improve the architecture and derive a kind of structure such that it suits our application purpose is the main thing that we like to emphasize. So accordingly, we have made some of the things and finally predicted for their classification. Now this is the same area, but crops are two different crops. This is, for example, let us say one is brinjal. This is, let us say, brinjal crop, and this is tomato. Then how to differentiate? So the very same network has been differentiating the two crops against the soil background. And similarly, if that particular image contains three different images, for example, the sand color is cabbage, and then that violet is brinjal, and this other one is tomato. So then what happens? You have not been training each and every time differently. Once you made your network trained to handle different scenarios, then its prediction is tested for. And if you have a two quite different image, for example, the same network where the composition of images or the spatial distribution of crops are different, how it is responding. So like that, it has been tested on different scenarios and made to see that some of these crops are predicted with pretty much accuracy, even though you infuse data sets of different altitudes. So that way, you notice that there is some sort of, let us say, stability of learning involved in this deep machine learning technique compared to any statistical prediction problem. So that way, we can conclude that there is something that you can tell about potential automation in regard to classification of crops at perhaps plant level with a deep machine learning technique, provided you get to go with a lot of image training that is there. So that has been assessed and it established it in this particular piece of work. Then the second application that we like to also put forward is that this in the previous case we have analyzed and implemented, but how much time it took for us to let us say realize the outcome given the input. So it would be order of several hours or sometimes even it's a couple of days. But in reality, nothing waits for us for several hours or days. So the things should be done on the go. In that case, similar kind of problem, for example, a classification problem, if you like to see that it is done on the go. So what is the case that is also has been explored? It is mainly from this real-time interpretation perspective. It could be in let's say single images, or it could be a stream of data where you would find that at every second you may find some 100 images as infused. So your outcome is that responding to the dynamic nature of your input data infusion, you should be getting the image analyzed on the go. So that is also one of the perspectives of this algorithmic handling. So usually what happens is that no statistical technique or a traditional even machine learning technique actually work the way you like to have on the go. Because when you like to see that these things are done on the go, you do not have the capacity to carry a big computer on your platform. So the hardware has to be extremely small so that the algorithms that are deployed algorithm are processed there and there, and the very small components are usually used for computation. So some of these reprogrammable reconfigured devices such as FPGAs appear seem to be one of the options. So if you like to have some sort of algorithms to classify or analyze images, then perhaps the possibility of realizing real-time image analysis is there. So we tried with one of the possibilities similar for FPGA-based kind of design of algorithms, and making this classification problem running on board is the thing that I like to show you some of the results. So here the emphasis is actually on this online classification. So as soon as image inserted, it should be in the sense infused, then it should be able to think. For this the algorithm that we have tried is actually this open set support vector machine. We initially started with the binary, but extended to multi-class SVM algorithm, which are trained on this ground-based data sets, and that they are all infused as a training library on this FPGA kind of thing. And the classification models are programmed to run such that even a small computer memory will do that. And then this system is fed to an input device, for example, an imagery acquisition device. Then as soon as image is acquired and which comes into the memory of this device, then this particular module of online training and prediction of the classification label is activated and it offers output on pixel by pixel basis. So this is architecture that is followed, and the typical algorithm that we have is SVM kind of thing. So we tested with few images, which are aviaris NG hypersphere images for land cover classification, as well as some crop images as well. Again, the drone-based imagery on typical land use perspective. And then again, the classes, no, crop classification using drone-based hypersphere imagery in the same data set that we acquired. Of course, we tried with different kinds of case studies, in the sense of different levels of crops, different growth stages, and composition of the crops in an imagery, where you will find a lot of image discontinuities in terms of the scale. So if you just look at some of the real-time metrics, you can see that the best time that you can produce an imagery, well, let's say output image, that's what, about 1 second, 1 second. So if you get one image per second, of course, you can respond to the classification almost the same time. But if the input rate is, let's say, 10 images per second, of course, then you're going to have a delay of few seconds to wait it. But the power that you're going to consume and the capacity that you have got to maintain on your board is actually very, very minimal. So that shows that if you are able to program this some of the hardware accelerators related kind of configure or reconfigure devices and train is library which which interacts with this real data and some typical let's say non-parametric machine learning algorithms are the classifiers. There is a possibility that you can actually do this real-time image classification. So that is one of the observations that we have made. And as you can see, different images which are there in the public domain, they have been analyzed and rated against their let's say data rate and time. Another application that comes into this one is the LiDAR point cloud. These days, it has been one of the commercially viable technologies which could be used for multiple kind of purposes. So we have tested again the same LiDAR point cloud classification for, let us say, classification for the agriculture related things, which involve two kinds of application. One is a classification, the other one is a prediction. So depending upon the kind of problem that we have, either classification or estimation, so accordingly, these machine learning algorithms have been chosen. For example, we show two examples, which one is the classification, other one is estimation. And the level is that this is an individual plant level. So that is the complexity at which we deal with this LiDAR point cloud analysis. So we acquired several LiDAR point scans at different growth stages. Actually, every 15 days, every 10 days, multiple scans have been acquired over the same experimental plots, and even crops of as much as only 5 centimeters have also been captured in the point cloud. So after a lot of pre-processing point cloud registration, we have generated finally one data set which contains all the crops and the same point cloud related only to the points, crops, and that has to be analyzed. So that is where the question of the algorithmic relevance comes. So as it is time series data, you would be knowing that how this crop is developed by phenology can also be answered we model the way this crop growth is taking place. So as you can see, some of these process data which patterns to two different periods of time. This is brinjal taken at two different dates. As you can see how this particular crop has evolved, and you can see some of the metrics. So if those things are there at point cloud level, then how we are going to predict them, classify them, and estimate some kind of parameters. So is that thing. So typical common steps included some of the filtering, then three-dimensional segmentation of point cloud, then estimation, that is crown area and the height estimation problem. So there, either you can go for machine learning or statistical or deep machine learning. So we see that it is not that much, let us say, attractive to go every time with, let's say, deep machine learning. The reason is that whenever you like to have any modeling done for estimation, the kind of reference data or sample that you require is a function. So you will not be having thousands of laboratory or field samples measured. In that case, you are going to go with only some of the machine learning applications which are okay to deal with. So in this particular case, though we have some samples which are quite good in number compared to the area that we have, but by algorithm they are really very few. So it is not imperative to use any deep learning for sense. So that way, this support vector regression, this machine has been used as a regression and then estimated some of the problems. So this is a methodology that I like to have. And of course, this is a pre-processing where you identify crown tops. And then finally, predicting different parameters such as, for example, crop height. What is the height of plant at each growth stage and how it fares well with the measured plant height. Similarly, biomass. So again, this is another prediction of the estimation problem. Known that your plant height is known, perhaps its crown area also estimated. Then, if you like to estimate biomass of that plant at different temporal periods, this is one of the applications of using this traditional machine learning algorithm as a classifier as well as a predictor, so that you will have the plant level estimates done. So that is one of the applications that has been tested for this. And you can see again at the same time how these estimations differ by the lesser nutrient level. Ultimately, we like to see that if we can identify plant type and its status, by the nitrogen level. So if that is possible with removal techniques, then a lot of application, operational application can be derived. So that is the motivation for us to do this kind of thing. And then further moving on to this one, whereas in this case we have tried to predict and estimate the parameters. In this case, we try to use some of these very deep CNN architectures with slight modification wherein you actually deploy this entire point clear on the go. Because some of these deep learning algorithms have been tested and developed for indoor kind of scenes where the point cloud is not a typical LiDAR point cloud, but point cloud acquired from other 3D devices such as let's say NIR stereos like that. But when it comes to a landscape-based kind of 3D modeling, it is here difficult to go with because the kind of object that you have, the point cloud and its number and density is so huge that it is not simply applicable whatever that is done in indoor to this kind of thing. So you need to find out a way where these algorithms are actually adapted and modified to respond to the point clouds of a landscape. So that is where you are actually going to adapt and modify the deep learning methodologies which work for this remote sensor related point cloud. So this is a common processing involvement. And after this, differentiation of canopy height model, you are going to deal with this deep point cloud model. So somehow the point net architecture has been modified to uh, take the entire point cloud as input, which is segmented, and produce an outcome which is plant level classification as the outcome. So that is the thing that is done in this case. And as you can see, so this is one of the typical architecture that have been used. So both the LiDAR point cloud as well as its RGB images are actually fused so that you'll get both, let's say, structural parameters as well as some of the color metrics which come only from RGB, the sensor. So with that, one attempt has been made where you can use the very same CNNs for segmentation as well as classification. So if you see that this is the plant level classification done with deep CNN. And this also have been compared with the other graphical based deep CNN methods and typical point net method, which you use directly as it is without any modification. So you find that things are looking better, but you will also find that you have a certain kind of inaccuracy as well. So you cannot be easily generalized in that adaptation of a deep machine learning directly works in a stable way. Still is the case. So some of the metrics show that the performance is reasonable, but how this performance varies when you have got a quite different, let's say, context has to be seen. And then another application that continuation of the same thing is that if you have access to point cloud and multispectral imagery. Sometimes this is important because whatever that you observe at the field level or plant level is not going to directly upscale at a large area. Because if you like to do any kind of mapping or modeling or any kind of prediction over a large area, you will have to use obviously a satellite based platform, be it optical imagery or even some sort of let's say LiDAR point cloud as well. So in that case, there is a possibility that the kind of features that you would like to get may not be retrievable from only one source. For example, if you are going to use LiDAR data, you get all these good quality geometric features. So two different objects which are geometrically different can be easily modeled using LiDAR point cloud. But if two different objects are structurally similar, for example, geometrically similar, but they differ spectrally quite different. If they differ by material nature, then this LiDAR particle cannot offer you any sort of discrimination. So that comes mainly in the spectral features. So two different objects which are quite looking similar can be having quite different spectral properties. So which would be the key for you to differentiate. So in that case, at times you can have a case where you take the benefit of both of these approaches together, such that you have got this geometrical feature and spectral features, and now try to enhance your discrimination ability. In the previous case, when we used only point cloud to classify the crops which are specific to, let's say, nitrogen level, we found that classification is happening. But whether the classified crop is, let's say, low nitrogen or high nitrogen, we cannot say that. So that discrimination is not there with that, in the sense with precisely. Because sometimes and a crop which is treated with low nitrogen is as good as a crop which is treated with high nitrogen. So in that case, you cannot differentiate with geometrical features alone. So in that way, a method has been tested whereby some of these common, let's say, machine learning approach such as random forest algorithm has been tested to integrate this classification process at the object level and the features that are there from point cloud as well as the very high resolution multispectral imagery, world view imagery has been combined and finally used to classify these agricultural crops which are at object level, plot level, and should be specific to different kinds of nitrogen treatment. So that is the application that is done. So this is the general approach. And finally, typical segmentation and rasterization is done. And finally, classified to give you an outcome which is at a field level. So finally, a combination of these tools have been done which will give you an object-based classification. Now, if you see, with different crops with different kinds of nitrogen levels have been taken care. So, this case, this is possible with this random forest, or it would also be possible SVM. But the sense of this deep machine learning could not be adapted here. We tried it, but the results were miserable. The reason was that the number of patches that are there very distinct for each crop at different nitrogen level actually very limited in number. So no stable learning is achieved in this deep medicine level. We tried few architectures, but none of them even respond to the way we wanted. So we observed that some of the traditional machine learning approaches seem to be a better option. And interestingly, this popular random forest algorithm has been observed to be one of the best still. In that case, we see that despite a few misclassification, most of these crops are now identified with a nitrogen status as well. So that indicates that sometimes your data also has to be having capacity to offer the features and also your ability to find out an algorithm which responds to your restricted data variety has to be kept in mind while we devise any application. So here in this kind of limited case, no deep machine learning actually works. And when you remove this, for example, the specificness, then the accuracy will be much higher. You get 100% if you don't care about the nitrogen level or if you are only going by, let's say, crop time. In that case, both is deep machine learning and traditional learning as well as statistical techniques also perform almost similarly. That is one of the observations that we made into this thing. I skip some of the metrics. And then the last application that I like to share with you is that uh, this is a kind of modeling problem, estimation to modeling problem. As I indicated at the start, the problem of having sufficient number of sample trainings is the biggest issue, in fact, in remote sensing related, where you like to adapt some of these deep machine learning algorithm. For example, we try to apply any airborne hyperspeed remote sensing for water quality parameter estimation. For example, if you like to let's say characterize the quality of freshwater lakes, then what happens is that you are going to determine several water quality parameters which are perhaps having response to optical properties of water. Not every property or every parameter is optically active. So the parameters or we say the components which are optically active can be attempted to retrieve using remote sensing data. So that way, if there are some important water quality parameters which are optically active, then if you like to estimate them with this Edmond hyperspectral data, then you will have the ability to apply, let's say, an advanced remote sensing for freshwater lake monitoring, such kind of thing that include a lake, reservoirs, or even rivers as well. Then what happens is that that is a typical estimation problem. It has been well studied in the case of traditional approaches as well as some of these statistical problems. But statistical problems are very specific to site and let's say data. So if you change the different data, perhaps your model is nowhere to respond. So in that case, if you think that some of the deep machine learning models can have some sort of ability to generalize the learning so that they can predict based on the training and can have predictions on unseen data, then what happens is that the kind of reference sample that you require, reference samples, it does not mean that the pixels imagery, but your laboratory measurements of water quality. For example, in this particular case, we have got about 105, close to there are 120, but few were not so quality, so we ignored them. Approximately 100 water samples were there, which were extracted from this lake, which is an example in Kerala, this Vembanadu lake. Now, by number, the 100 water samples is a big number. In fact, it's a very big number for any traditional testing on the same day. But if you like to think of any machine learning approach, then the 100 is a very small number. The reason is that the dimension of your data is so huge, you have got even after pre-processing and elimination, you may get about 350 number of spectral bands in every NG hyperspectral sensor. And in addition to that, to impart any meaningful training for your network, you take any either advanced or primitive network deep machine learning approaches. They require at least 20 times of your dimensional of the data. So if you have got let's say 300 as your number of bands, and then you have got 20, so 20 into 3000, 300 is the kind of dimensionality, the sample dimension that you are going to get to have any stable or transfer learning imparted to any deep machine learning. That is what the some of these evolving theoretical approaches predict. In that case, that particular deep model will be very stable in its prediction, so it can work. In that case, what happens is that our 100 samples are actually nothing. So you get 100 pixels for modeling, and at each one pixel you call one measurement. So you can maximum try with typical statistical methods, which are good for only local predictions, and you cannot even go for any kind of machine learning approaches in principle. So how to move around that kind of problem is the problem that is attempted in this case. So we have taken, let's say, even a ground-based hyperspectral imagery, which are abstract for some kind of ground-level images, which where we will have control over image relations as well as the tuning parameters. Then on the same day, here one hyperspectral imagery and water sample have been taken and extracted and analyzed. So now the problem is to predict certain kind of water quality parameters based on deep machine learning approaches. Now we know that the number of samples that we have are very limited. So obviously we cannot go. Then what is the method that we should be devising so that we can adopt such kind of thing? So in a typical case, this is a statistical way of looking at. So you have got your data and your lab analysis. Maybe you do some sort of reprocessing to the imagery, and you can adopt any one typical statistical technique such as the partial least square analysis kind of thing, and you can split the very same 100 samples in training and testing and make a statistical model and validate it. So you get a kind of prediction model that may be good for that particular day and time. So if you like to change the data, then obviously it has no value. So in that case, how to deal with is the case that for that what we have done is that we have used actually two kinds of innovation here. One is this augmentation of these objects. Actually, that is the key here. Okay, what we mean is a guided object-oriented deep learning means when we have got only 100 locations, each location is 1 pixel, so 100 samples which are water samples, how to make the 100 to let's say some 10,000 or 5,000, like that is the case. So for that, we have made a kind of approach which used actually some of these implementations of genetic algorithm which predicts, which actually works the way we like to enhance the relevance of spatial neighborhood. So we know 100 locations. So around each location, we carve out a patch. We are image patch. So let's say about some 7 pixel by 7 pixel carve out a patch. So within that patch, we like to predict what is the pixel which is very close to the actual patch, actual pixel within that same patch as the prediction. So for that, some of this subjective SVM regression has been used to find out the pixel which is very close to that. Then we have got from 1 pixel out become 2 pixel. So repeat the process with one more iteration such that you have got a few pixels in each patch which represent somewhat statistically closer to the actual reference pixel. And then deploy a genetic algorithm which actually iteratively works to generate a set of images, image patches which represent different levels of this water quality patches. So when we deploy this genetic algorithm in this fashion, what you are going to ultimately get is that around each original patch of 100 pixels, you are now going to get several thousands of those image patches, which are statistically very closer, or spectrally very closer to the pixels, which are actual pixels of this water quality sample location. So that way, when you combine this genetic algorithm based way of optimization and support vector regression kind of prediction within the local neighborhood, you are going to get an image patch which is almost equivalent to your original ground location patch, such that your ability to have the number of training pixels is now much better. So the 100 now become 500, 5,000 pixels now. Now, once you reach that level, you can actually run any deep learning architecture, which again we have used some of these object-based CNN architecture to give these image patches and predict on the image. So again, once we get those many number of patches, those are used for training as a network and carve out any common network and allow the network to predict. So that way, we have made this water quality mapping problem from 8-1 hyperscale imagery, despite having very fewer number of training pixels. So the way we like to look at it that how do we guidedly select the pixels and finally propagate to a level where you are going to get several thousands of pixels which are very closer to the actual ground location, such that mathematically you can enhance your training pixels to the rate required for running any deep learning algorithm is the novelty in this particular thing. So like again, we predicted some of the parameters, very common water quality parameters, and again compared with some of these typical machine learning algorithms, and just made how they actually fare against each other when we use only deep machine learning and when we use only machine learning approaches and some of the statistical approaches as well, and compared with some of wherever locations are possible compared with actual measurements as well. So somewhere you will find that some sort of convergence is there. If the parameters are optically active, the level of prediction of these water quality parameter by definition is very fair. Somewhere this parameter is a little bit inorganic and is not spatially correlated. Then despite meeting your dimensionality and despite your deep learning algorithm is trained to handle different parameters, it still produces not so nice results. That is one of the observations of this one. And I like to close my thing. See, generally what happens is these conclusions are something like that. They're always the way we like to optimize the networks, optimize the system, and how you infuse data. Most of the approaches that have been, shown in these publications of across worked on based on very small patch of images. No operational work actually happens on a small scale. So an image of 20,000 by 20,000 pixels is very common in operational applications. So if you like to apply any machine learning or deep learning algorithm for any kind of application, then the factors to be considered are should be your network should be ready to handle the entire image as a whole. There should not be a small patch, then work on that to say that the result is good. It is not going to be good for practice. It may be good for only a publication. And then another is that how to optimize this computation and training your prediction thing. It should not be several days of running. Unfortunately, if you see, most of the algorithms run for hours to days. In that case, no operation remote sensing algorithm is actually useful. So we should be having an optimization of these algorithms, which included the way you deal with architecture, the way you infuse the data, and the way this data are pre-processed before it comes into this prediction stage are vital so that your prediction is happening on minutes basis or preferably or ideally on second basis. And the last point that I like to stress is that despite having your good algorithm, it would not be useful for anything unless otherwise you train it extensively. And this extension training has to be readapted to your application imaging. So if that is not opened up, then the observations show that deep machine learning will actually deep disturbance problems. Instead of helping us, they actually disturb the way you get the results with statistical or traditional machine learning approaches. So with that, we should be careful of, let's say, absent-mindedly applying any algorithm on this kind of application. So we should be knowing where they were, should be knowing what are the limitations that we have, and to find out the opportunities where they are really potentially suitable compared to other things. So that's what.